Hi, this is starting chapter 10. We're going to go with section 1 today and talk about the kinetic molecular theory as it pertains to gases. So, kinetic molecular theory, the word kinetic means to be in motion, so we're going to talk about molecules in motion. And for this, we're going to look at ideal gases first. We're going to look at the difference between ideal and real gases. Ideal gases have 5 different things going on with them. Number 1, they are considered to have no volume. So for an ideal gas, there's a lot of space between molecules, so no volume there. Number 2, they will have elastic collisions. So within a gas, molecules are colliding around. Even if they collide with each other, they will just bounce off, move in another direction, not slow down, not pick up speed. Elastic collisions. Number 3, these molecules in a gas are in constant random straight line motion. They will not attract or repel each other. So even if during their elastic collisions they collide with each other, they will not attach themselves to each other. So no attraction or repulsion. And they will have an average kinetic energy directly related to temperature. So their kinetic energy is directly related to temperature. That means if their energy, their motion increases, then the temperature of that sample of gas will increase. And the reverse is true. If you decrease the temperature, then the motion is going to slow down. So they do move relative with each other directly. So that's for an ideal gas. If you have a real gas, these particles do have their own volume. These are typically going to be more massive gas particles, and there will be some attraction between those gas particles. So if you want your gas to behave ideally, you need 3 things to happen. You want a low pressure, a high temperature, and a non-polar substance. We just talked in chapter 6.5 about those intermolecular forces, your London dispersion forces, dipole-dipole, hydrogen bonding. So for a real gas, you're going to talk about things that are typically hydrogen bonding is going on. Definitely the dipole-dipole because they're the heavier molecules. So for an ideal gas, you are looking for a non-polar substance, preferably, to get that gas behavior. Now, some other characteristics of gases: they will expand to fill any container. This is due to their random motion, no attraction going on between molecules, so they are just constantly moving around. The gases are considered fluids, just like a liquid, because there is no attraction between molecules, and gases have very low density. Again, lots of empty space. If I refresh your memory on the density equation, density is mass over volume. If they're going to have a very low density here, then you want what is considered to be a high volume here. So when we say no, don't let that be misleading here. It's a very large number or large volume that you have. It's just a lot of empty space. A lot of empty space that is not necessarily the gas that you're looking at. So if you can have a low mass, high volume, you will get a low density. Very commonly for your gases to have density that are much less than 1, because we think of water as having a density of 1. So your gases are going to be much lower than that. And this right here, it's showing you in a closed container. This would be a solid. Let me pick a different color here. Solids right here, closely packed particles. This is going to be a liquid. The liquid, your particles are a little further apart, but notice they do take up the edges of the container here, flow freely over each other. And then our gas right over here, it does take the shape of the container. Looks like you have tails on the end of it, showing you the motion moving much faster than your liquids. And a couple more characteristics. Compression, gases can be compressed. Again, all that empty space, if you want to take it away, you compress a gas. That means to push the molecules together. And also, I'll talk to you about the difference between diffusion and effusion, get some more definitions down. The picture that's here on the left, it's showing you a piston and lots of empty space in here, but if you push down on this and get all those particles packed in close together, you take away that empty space, you have compressed your gas. It is now under a higher pressure. And in the picture on the right, well, actually two pictures because we have a couple different things going on. This is diffusion. Diffusion happens naturally with a gas. It is a much slower process. They're showing you there, think of that as being a perfume bottle. They have opened up the lid to the perfume bottle. Those molecules automatically, because the gas molecules are moving and a lot of perfumes have alcohol in it, which alcohol becomes a gas at a much lower temperature than, say, water does. So it is turning into a gas too. Those molecules will freely move out, and if you were across the room from me and I opened up a perfume bottle, at some point soon you would be able to smell it due to diffusion. Whereas the picture that is over there on the far right, this is effusion. Effusion, I put one too many S's in there. Effusion is going to happen when you have a tiny opening in a substance. This right here, think about you putting a hole in a balloon and you have a quick escape of particles through that tiny opening in whatever your material is that you're working with, and the gas particles are escaping through that tiny opening. So that is the process of effusion. It is a little different from diffusion.